Welcome to Instrumental Analysis, GMT20230803. We're going to cover this course. It's fast-paced with a lot of chapters. And this is the lecture number 1 on the introduction. So as you notice, this course is instrumental methods of analysis, or it's called instrumental analysis. I'm going to give the introduction here. And we're going to cover the types of instrumental methods that we use in this introductory chapter, the fundamental components of an instrument, and what instruments measure. They measure voltage and currents. And first of all, I would give some basics of the analytical methods, a quick review of some of the terms that we have used. You have seen these terms when we went through the Analytical Chemistry 1 quantitative analysis. So I'll give a review of some of those basic terms, the terminology, and a review of what you already know. Some notes and the figures in this course have been taken from Skoog, Haller, Newman, and Crouch, which is the Principles of Instrumental Analysis. You can use the 5th edition, 6th edition, or the 7th edition by Saunders College Publishing. So again, notice this is a summary of what we are going to do here. Now, let's define the analytical chemistry. We want, first of all, to define analytical chemistry. Instrumental analysis, as you know, is part of analytical chemistry. So analytical chemistry, by definition, is defined as the science and the art of determining composition of materials in terms of the element or a compound content. I repeat, it is the science and the art of determining composition of material in terms of the element or the compound content. We are simply concerned with chemical characterization of matter, and this involves both qualitative and quantitative determination. And therefore, as we go about determining or characterizing the content of materials, we need to be aware of the classification of the analytical methods that we use. Analytical methods can be classified into 2 broad categories: chemical methods, or the classical methods that were used before. And then the other type of the analytical techniques will be physical methods, which are essentially the instrumental method. And so let's start with some of the chemical methods that we use. These are called the classical methods, as noted in the previous slide. So some of the classical methods that have been used before were the gravimetric method, where you weigh mass. The other one is volumetric method, which involves titrimetric procedures. And all of us at this stage, we have been exposed to titrations. That involves measuring the volumes of your analyte and the titrant. So you're exposed to volumetric methods, which can be classified as acid-base titrations. You use neutralization methods, strong acid, strong base neutralizations, or strong acid with base neutralization, as it may demand. The other type of volumetric method will be the oxidation reduction titrations, which involve redox type of methods. The other one for volumetric methods will be on precipitation titrations. And as well, we can use titrimetric measures or volumetric methods to follow some complexometric titrations. And if you may remember, you have used some EDTA type of complexometric titration where EDTA binds to metals. Now, I've briefly talked about the chemical methods. Let me briefly talk about the instrumental methods or the physical methods. The instrumental methods can be subdivided into these categories: the optical methods, the electrochemical methods, and some miscellaneous methods. So let's look at each one of these separately. So before I look at each one of them, there is some chart given in your textbook, which is very useful for us to just try to understand what is involved in chemical and physical properties that are used in this instrumental method. This is table 1.1 in our textbooks. You will notice some of the characteristic properties that we are after and the instrumental methods that use that particular characteristic. For instance, if we are concerned with the emission of radiation, then instrumental methods that rely or use or make use of the emission of radiation will be the emission spectroscopy, for example, X-ray spectroscopy, UV or visible spectroscopy. They can also involve some emission of radiation, the electron emission spectroscopy, or Shea type of spectroscopy. Fluorescence is an emission type of radiation. Phosphorescence is an emission type of radiation. Luminescence, which can also, where you get some analytical techniques such as X-ray luminescence, UV visible luminescence. So we make use of the emission of radiation. We have another broad category of these analytical techniques, that's the absorption of radiation. That's the electromagnetic radiation. And this involves spectrophotometry and photometry. We have X-ray radiation. It's an absorption phenomenon. UV or visible type of spectroscopy. That is an absorption of sunlight. Infrared radiation. Or when we use infrared spectroscopy, we're making use of compounds absorbing light, the electromagnetic light, in a certain wavelength. Photoacoustic spectroscopy is also useful in this manner. Nuclear magnetic resonance, NMR, electron spin resonance, spectroscopy, all these are absorption type of spectroscopies. If we are interested in the scattered light, scattered radiation, we can use turbidimetry, nepherometry, or Raman spectroscopy, which is widely used in characterizing materials. We also talk about reflection of radiation, in which we get such instrumental methods as refractometry or interferometry. Now, we talk about using the diffraction of radiation in probing or characterizing materials. Diffraction of radiation, where we use X-ray diffraction or electron diffraction methods in characterizing materials. We also talk about rotation of radiation, in which case we talk about polarimetry, optical or tertiary dispersion, or circular dichroism. Now, there's one other thing. Notice these top ones here deal with the radiation, the electromagnetic radiation. You can also talk about a current, the electrical potential meaning voltage, in which case, if you are measuring the electrical potential or electrical voltage, then you use potentiometry. You're measuring the voltage. to give you information about the analyte. And then we talk about chronopotentiometry. If you measure the charge, electrical charge, then we talk about an analytical method, and this is an electrochemical method known as coulometry. If you measure the current, then we have amperometry or polarography that we use in instrumental method in analytical chemistry. And then if you measure resistance, then you're measuring the conductometry, and you can measure the resistance of any given material and characterize that particular material. One particular important characteristic property that we often use in measurement is the mass. The mass can be used in measuring the mass of the substance of the analyte or material, and that is referred to as gravimetry. Gravimetry has been here with us for a long time. This is the basis of the quartz crystal microbalance. Now, there is one other analytical technique widely used in biological samples, in environmental samples, and that involves the measuring the mass to charge ratio of your analyte. And that's where mass spectrometry comes into play. It's widely used. Now, if you want to measure the rate of a reaction, we talk about the kinetic methods. Now, there are other methods that make use of the thermal characteristics. Thermal characteristics, in which case we talk about thermogravimetry, TGA, and titrimetry. We talk about differential scanning calorimetry, DSC. We talk about differential thermal analysis. We talk about thermoconductometric methods. These are thermal characteristics. They make use of heat. You heat things depending on temperature. And radioactivity also is used in analysis. Some materials are radioactive. So in which case we talk about the activation type of instrumental methods or isotope dilution methods. This is a summary of the chemical and physical properties that are used in instrumental methods. At the end of this slide, you notice at the very bottom here is a block diagram that summarizes what really happens in analysis. You usually have a stimulus. A stimulus is what is going to interact with your material. In many cases, it's an energy source. And then you have the system under study. It can be a solid, it can be a liquid. Nevertheless, the energy source is directed at this system. You must have a stimulus, some form of energy, some form of current, which you direct onto your system under study. And then from that, you get a response. The response then is interpreted as an analytical information that is useful for analysis. So this table here is important. Make sure you understand the three categories of types of characteristic properties that we probe. Materials for radiation. We use radiation. We use some voltage. We use some charge or current, or resistance or mass to charge ratio, or we use some thermal characteristics to tell us about the behavior of any one given analyte or substance. Now, I'm going to present another table here. Here are some examples of instrumental components. And this table is going to be very useful as we proceed. Maybe chapter 6, 7, and we present these again. And we repeat these again when we get to that chapter. Now, first of all, here's some examples of instrumental components. Here is an instrument. You have a photometer. The energy source, the stimulus, as we have said previously, the energy source, which is a stimulus, is a tungsten lamp. The tungsten lamp is then going to give us provide some attenuated light beam, some light beam that's going to be absorbed. It's going to be directed to your sample. And then from there, you need to sort that information. You get an analytical information from the light, and you need to choose the light that's going to be useful. Therefore, you use a filter to filter all the light. And then you need now to direct. The filter sorts out the information, and then you have an input transducer. The transducer, another name for a transducer, is a detector. So you use a photodiode. Then you interpret the data from a photodiode, you change then in the information into an electrical current. So the data domain of the transduced information. Then from there you have an amplifier or a digitizer or an LED display which is a signal processor. That is your readout. Now let's talk very quickly about the atomic emission spectrometer. So the image source for atomic emission, for example, in inductively coupled plasma. So the analytical signal is usually in the UV, all the visible radiation. And we use a monochromator just to choose or to sort the information, the wavelength that is going to be used for analysis. And then you get a photomultiplier, which is like a detector, which amplifies that signal many, many times, a PMT. Another name for a photomultiplier is a PMT. And then we have the electrical signal, in which case you get the electrical signal from the photomultiplier, then that is digitized, and the information is amplified. These are some simple examples of instrumental components. You have a coulometer. Coulometer measures direct current source, and we measure the charge required to reduce or oxidize the analyte. That's the analytical signal. And then you can have, in a coulometer, you can have a cell potential. You must have electrodes. And often in coulometry, the data domain of the transduced information is in time. From there, you have an amplifier and a digital timer. Now, you all know about the pH meter. pH meter is used to measure pH, and the image source or the stimulus in the pH for measuring the pH using a pH meter is the glass electrode or sample or a glass electrode. And often in pH, we are measuring the hydrogen ion concentration or the hydronium ion concentration. Roughly, we approximate that to be the hydrogen ion activity. Really, its activity, as you all know, it's not really concentration, it's the activity of the hydrogen ion. Then the information sorter is the glass electrode that is sensitive to the movement of the hydrogen ion across the membrane. Now, there are several input transducers. You can have a glass calumet electrode. You can have a silver chloride electrode, many other electrodes that you can use. Eventually, you get your data domain of the transduced information. You get the data that you get from there is an electrical voltage, and then that electrical voltage then can be processed. And what you read out, or what is going to give you to process that electrical voltage, will be the amplifier or a digitizer or some form of a digital display. Now, let's talk about the mass spectrometer. In a mass spectrometer, really you are measuring the mass to charge ratio of your analyte. That's the analytical signal. Now, the image source in a mass spectrometer is the ion source. You must have an ion source that's going to ionize. The ion is ionized. Usually it's the filament which provides electrons to ionize your analyte. So the analytical information we get is the mass to charge the mass to charge ratio. and you sort your information. The information you sort when you are using a mass spectrometer is the mass analyzer. You are sorting masses. And those are the masses that tell you about the molecular ion of your analyte. Then you can have a signal transducer. The detector is an electron multiplier, and the electron multiplier amplifies the number of electrons. Then from there, you get the electrical current. And then you have the amplifier or the digitizer or a computer system that's going to act as a signal processor. Now, some of you might have dealt with a gas chromatograph with a flame ionization, a GCFID, for example. So the flame will be the stimulus, and then you have the analytical information will be the ion concentration versus the time. And the sorter, whatever it sorts all the various ions, will be the chromatographic column. The column sorts that information so that you have peaks. And you have an input transducer, which will be a biased electrodes. Eventually, you get an electrical signal, and then you can translate that electrical current to peaks, what we call peaks or bands. So these two slides, table 1.11 and 1.2, are very important in understanding some of these things, and you will be faced with this in this course. Now, remember the various types of instrumental methods. Let me go back for you to see again, refresh ourselves. Instrumental methods or physical methods can be divided into the optical methods, electrochemical methods, or some miscellaneous methods. So let's look at the optical methods. What are the optical methods then? Optical methods can be divided into various types, but the bottom line is in optical methods, we make use of the interaction of the electromagnetic radiation. And this the electromagnetic radiation can be absorbed, hence absorption. Or the interaction of the electromagnetic radiation will mean that that electromagnetic radiation, there is emission of the electromagnetic radiation. So, or that when your analyte interacts with the electromagnetic radiation, there will be scatter or a refraction of that electromagnetic radiation, or that type, there will be some rotation of the electromagnetic radiation. So optical methods can be divided into the absorption type of optical methods, emission type of optical methods, the scattered type of optical methods, or rotatory type of optical methods. And all of them are based on the interaction with the electromagnetic radiation. The absorption type of optical methods will involve UV visible spectroscopy, infrared spectroscopy, NMR, X-ray spectroscopy. These are some of the methods. These are absorption type of methods. They absorb light. The emission type of methods will be fluorescence, phosphorescence, flame photometry. Scattering type of optical methods will involve interferometry, turbidimetry, Raman spectroscopy, or refractometry, where light is reflected. And those kind of analytes that might rotate light, then we make use of the rotation of light in polarimetry. Now, that is on the optical methods. Let's deal with the electrical methods. Electrical methods will involve such methods as measuring pH and potentiometry, conductimetry, voltammetry, polarography, amperometry, and coulometry. So these are the type of methods that we use. We have electrochemical methods. And then miscellaneous type of methods would involve thermometric analysis, the DSC, differential scanning calorimetry, or thermogravimetric analysis, TGA. Now, what are then the advantages of instrumental methods? What are the advantages of instrumental methods over classical methods? You can think about many. One will involve high sensitivity. Instrumental methods are highly sensitive, or high accuracy. The other will be, we normally use small samples. We can use small samples that can be used for analysis. The measurements obtained normally are reliable and reproducible when we use instrumental methods. Normally, instrumental methods are fast. We have fast determination, and complex samples can be handled very easily. These are some of the advantages, as you see here, of using instrumental methods, and you can automate the process. The process can be made automatic. You can automate it. So we've seen some of these advantages of instrumental methods, but they also have disadvantages. What are the limitations of instrumental methods? Number one is the high cost. The high cost of buying instruments. It is also necessary to use reference substances. And number three, you need skilled persons to run the instruments, or persons who are trained. And so these are three disadvantages that we can think about. Now, I've already pointed you to some basic instrumental components. And I want to amplify this again. What are the basic instrument components? If you remember, in one of the previous slides, there was a very, very brief diagram under table 1.1. You need a source. The source is going to produce a form of energy or mass that is relevant to the measurement at hand. So you need a source in an instrument component. Number two, you're going to need a sample holder or a cell. This is going to contain the sample with your analyte of interest. And you need a discriminator. The discriminator is going to select the desired signal from the source or the sample. The other thing, one other instrument component, is the input transducer. The input transducer detects the signal from the sample, the signal from the source, or the discriminator. It detects the signal from the sample, the source, or the discriminator. It's also known as, AKA, the detector. It's known as the detector. So once that happens, then you have to process your data. Once you have an input transducer, it detects your signal from the sample, then you need to process that signal. So the processor manipulates the signal electronically or mechanically to produce some useful value. And finally, you get a readout, a display. A readout will display the signal in some useful form. It can be peaks, you can digitize it, and then we talk about peaks and then concentrations. Now, as an example of the basic components, this particular diagram, which you can find in your textbook, runs through all these components. Number one, you have an energy source. So the figure A, the top diagram here, is a block diagram of a fluorimeter showing a general diagram of the instrument. This is a fluorimeter as you would normally find in any lab. So you need an energy source. and a laser can be an energy source. And notice it's directed in tonic water. Tonic water, there's an analyte in tonic water that we may be interested in. And then you notice fluorescence. It's an emission phenomenon. And so fluorescence directed at this optical filter, the filter is going to choose particular information and distinguish the signal from the analyte. So you need an optical filter. And then you need a phototransducer. So this whole diagram here, you might recognize this as ohms, a resistor. And you have the voltage across the resistor, the voltage. You see the resistor here, and then you have I, or current. So you are measuring this, and then using Ohm's law, then you get a digital voltmeter to measure the voltage. So you have an energy source. You have your analyte, as we've said. So refresh ourselves. You have a source, a sample holder, a discriminator, an input transducer, and a processor, and then a readout. So this is what we're having, a source here. Now, part B of this block diagram, it tells you on how this information is transmitted from one end to the other. So you get the information flow, you have a source intensity, and then a source intensity, then you get fluorescence intensity of your analyte. So the analyte is in this tonic water, for example. And then that intensity of the analyte is going to be you would have, you notice here, you're going to have a current on this resistor. So that will be the electrical current, I, or that can be changed to voltage, and then you read a number. Electrical current can be changed to voltage using Ohm's law, V equals to current times resistance. Then you get the number here. So the number you measure is simply the voltage. So notice part C, these are the rules that govern the data domain transformations during the measurement process. What are the rules governing the data domain translations or transformations? These are governed by laws of chemistry and physics. And in this case, there is a transducer. And so the transducer has its function. And when we talk about a function, we're talking about the physics of that particular transducer. And then it's also governed by Ohm's law. Ohm's law, V, voltage is equal to current times resistance. And then we also have the meter transfer function. Whatever you measure, it has particular rules that govern how it's going to display the number that you get. So again, this is a very quick block diagram that tells us about the laws that govern what you'll see. Now, instruments measure one of two things. And what are they? They can measure voltage or volts, or electrical potential across two electrodes. For example, this first one here, you can see they measure voltage across two wires here, across this resistor. And then they also can measure current. It's one of two things whenever you are getting some information using an instrument. It's current, A, which is measured in amperes, and current is the flow of electrons across some point. Those are the two things that we measure when we get our information. And it's governed by Ohm's law, V, that's the voltage equals to current, I, times the resistance, which is measured in ohms. So resistance is measured in ohms, as we all know. So now, thus far, we have talked about the various methods, instrumental methods. Let's address important questions regarding all analytical and instrumental methods. Number one, you have to define the instrumental analysis problem. what accuracy and precision is required when you are taking a measurement. Number two, how much sample do I have available? If you're going to go into the lab, you want to characterize that amount, that material. You want to know the quantity. You need to know what instrument you're going to use. How much sample do I have? How much money do we have available for the analysis? And as you know, it's going to take time. It's going to take complexity. If you want complexity, time and complexity is going to be equal to money. You have to put money in the analysis. It's time and complexity. What other question do you think about? Let's think about it. What concentration is the analyte present at? And can we pre-concentrate or dilute the sample? If the sample is in very trace amounts, then you need to gather a large amount of sample, then pre-concentrate it. Or if it's very concentrated, then you have to dilute the sample. These are the practical challenges of measurements. Other things that you have to worry about when you're taking a measurement. What are the interferences that might be present? You have to know the interferences that can be present, and can we eliminate or mask those interferences? What are the properties of the sample? The sample matrix. Sample matrix may interfere with your analysis. You need to know what the sample matrix is. And how many samples must be analyzed? Again, it all goes down to the second part here. How much sample do I have? That translates to time and complexity, which translates to money. How much sample, how many samples must be analyzed? And this normally quickly builds up, quickly adds up. Now, we've said about these basic questions that we ask ourselves. There are about 5 questions and any that you can think about. Now then, here is a review. In this review, we define some basic terms that you have already been faced with in quantitative analysis, introductory analytical chemistry 1. So instrumental analysis may be analytical chemistry 2. So what are the basic definitions? 1 is the term a sample. You collect a sample or you take a sample. An aliquot. An aliquot is usually selected from a larger bulk sample for preservation or for preparation and or analysis. So you take a small portion from the bulk and then you can preserve it. You can use that aliquot and prepare that aliquot, and then you can also analyze that aliquot. So another one is the technique. An analytical technique implies the use of a specific type of instrument for analysis. The other definition will be a method. Method is the procedure followed when utilizing an instrumental technique. And the other one will be a protocol. Protocol is a regulatory or officially recognized method that must be adhered to. So it's a protocol. You have to follow a regulatory or officially recognized method. And there are many methods that have been that are out there by various organizations such as US EPA. It brings out protocols that they have tested over and over, and we can use those for analysis. Now, let's make some definitions here, which you might be faced with later. GLB. GLP stands for good laboratory practice, and the other term is GMP, stands for good manufacturing practice. These are basic definitions that when you talk about analysis in the lab, it's a sample, it's an aliquot, a technique that you're going to use, the method which is associated with the procedure, or the protocol that you're going to follow. Now then, having said that, some of the analytical parameters that I'm going to talk about, you might have, you have faced them. What are the relevant analytical parameters that we talk about? Some of these are new. You should be familiar with the word accuracy. You should be familiar with the word precision at this point. An average, how to calculate a standard deviation, or percent relative standard deviation. These are terms that you've been exposed to. But here is one of the newer terms, analytical sensitivity. When you hear the word analytical sensitivity, you're talking about the slope of the calibration curve. That is the IUPAC definition. IUPAC, International Union of Pure and Applied Chemistry. IUPAC, International Union of Pure and Applied Chemistry. This is the definition of analytical sensitivity. It's simply the slope of the calibration curve. The other one, so you notice here how it's defined. Analytical sensitivity is equal to the slope of the calibration curve over the standard deviation of the measurement. It is just the slope. Now, thus, other factors being equal, when you look at the analytical sensitivity slope, the steepest slope usually, the steepest calibration curve will be more sensitive because the slope is steeper. For a very small change in concentration, then you have a big change in the signal. So if you have a better sensitivity, that will be a better ability to discriminate between numerically close concentrations. So we're talking of just the slope being steeper. So here is an example of what we are talking about sensitivity. Here are two methods used for analysis. One, UVVs in blue, and then you can see AAS, atomic absorption spectroscopy, this one here in purple, and look at the equation for each of these graphs. We are measuring a particular analyte Y in PBB. You notice the slope of the UVVs measurement, Y equals 0.204x plus 0.0018. Notice 0.2, this is Y equals mx plus c. Y equals 0.204. 0.204 is the slope. This is the line, the equation of a line. And then you look at this measurement here, same analyte measured with a different technique, AAS. Y equals to 1.0279x minus 0.0055. You compare the two slopes. The AAS has a larger slope. It's more sensitive for the analyte Y. The square bracket stands for molar concentration in parts per billion. So you notice UVVs, AAS, we're measuring absorbance here, right? And which one is the better technique for this kind of analysis? AA is better, is more sensitive than UVVs in measuring these analytes. And in general, it is true. Now, so we've talked about sensitivity. Let's talk about the detection limit, DL, LOD, or MDL. DL, detection limit, LOD, limit of detection, or minimum detection limit, MDL. So all of these terms mean the same. This is one of those most widely disputed term in instrumental methods. What is LOD? So let's define it. LOD is the minimum concentration of analyte that can be detected. and it's based on the analytical signal, the minimum concentration of the analyte that can be detected based on the analytical signal. The signal is a response. If you have a larger signal, that can be observed. Now, notice the word here, the operative word, is detected. Minimum concentration of analyte that can be detected. It can be detected. It's not necessarily known with any great confidence. The other thing is the LOD, C sub M. C standing for concentration. Concentration. You notice the minimum concentration, Cm, is equal to the square bracket. So that is the mean blank signal. This is the mean blank signal. It's the average of your blank. The blank will have a signal, but the average of the blank plus 3 times the standard deviation of your blank signal. So let's say, for example, in general, we take 3, these come from statistics, and I know from quant you've done this. In general, in quantitative analysis, in general, 3 is chosen as the multiplier because at plus 3 standard deviation, you are about 99% confident you are not measuring signal, or you are measuring the signal, you are not measuring signal from noise, the background, etc. What we are saying here is at 99%, you are measuring the signal. It's not noise. It is distinguishable from the noise or the background. And the measurements, so in a detection limit, those are measurements at or near the limit of detection, are not necessarily precise. So they have a high percent RSD, relative standard deviation. And usually, this is what instrument manufacturers will quote for you as a measurement under the most ideal, not regularly attainable conditions. Now, the standard deviation of the blank, notice how we define LOD, is the mean blank signal plus 3 times the standard deviation of the blank signal. The standard deviation of the blank signal is often replaced with the standard deviation from some very, very low near the detection limit. How confident would you detect your signal near the detection limit of the sample that you have prepared? So this signal is then used with the calibration curve to calculate a detection limit. So detection limit is simply said, you notice how we define it, is the mean, the average of the blank signal, plus 3 times the standard deviations of the blank signal. You are above, 99% above the blank signal. Okay. Now, another associated term will be the limit of quantitation, LOQ. This one is also disputed, a somewhat disputed term. But what do we mean by the limit of quantitation? So normally, the LOQ is generally considered the minimum concentration of analyte that can be accurately or precisely determined. The exact definitions vary. However, we can define it mathematically. So normally, the LOQ is equal to this bar here. The bar over the blank signal denotes the average. It's the average of the blank signal plus 10 times the standard deviation of a very low concentration sample. Again, I remind you of, in quantitative analysis, it was around chapter 5 of Harris, we went about calculating the LOQ, but this is how we define it. Notice the difference between LOD and LOQ is this value 10 here. For LOQ is equal to the average of the blank signal plus 10 times the standard deviation of a very low concentration sample. LOD is defined as the average of the blank signal plus 3 times the standard deviation of a very low concentration sample. So bear that in mind. We are 10 times above the signal, the blank signal. That's called the limit of quantitation. So in general, if you want to determine the limit of quantitation, you measure a blank and a very low concentration sample that is near the detection limit many times, and then use that data. 10 times is the typical number of replicates that we are going to use normally. And this signal is used in the calibration curve usually to calculate the limit of detection, or the minimum detection limit. So we have defined LOD and LOQ. Another term that we want to define is the dynamic range. Usually, this is called the linear dynamic range, and this is the concentration range over which the calibration curve has a linear shape. It's linear within that range. So you probably have seen this. You have seen an instrument exceeding its linear dynamic range, for example, with SPEC 20, if you are exposed to SPEC 20 spectrophotometer, which some of us, or you may be aware, we use for the general Gen Chem. So you probably have seen this. You might have seen that an instrument can exceed its linear dynamic range, for example, with SPEC 20. Now, remember what a dynamic range is. It's a linear dynamic range. It is the concentration range over which the calibration curve has a linear shape. Normally, outside that linear range, Beer's law fails at increasing concentrations. It might fail because of the sample matrix. It might fail because of the analyte or the method development. The method has not been developed well, or analyte interactions. You usually want to work with the linear calibration curve, or within the linear range, if at all possible. It's much less complex than fitting a graph into a quadratic, an exponential, or a polynomial fit. So you normally want to work within the linear range. So, for example, when we measure the concentration of metals using AAS, usually the linear range is within 1 to 3 orders of magnitude. The lowest concentration to the highest concentration is linear within 1 to 3 orders of magnitude, 1,000 times, usually. Now, if you measure metals concentrations by ICP AES, inductively coupled plasma atomic emission spectroscopy, then you have a higher dynamic range, 5 to 8 orders of magnitude, 5 zeros to 8 zeros. Okay. So here is an example, an illustrative example that shows us really what this dynamic range is. For example, here is a calibration curve for the absorbance measurement. Some analyte, take it, this is an analyte. So let's say it's an absorbance on the y-axis, is absorbance. On the x-axis is an analyte concentration, molar concentration. And when this experiment was done, it was found, this is the blue line here, 0 here, almost 0. You have this other point here, concentration. You have this other concentration here, or signal. Then you have another one here. Beyond this number here, then it's no longer linear. Notice you can draw this purple line. So this, at this point here, Beer's law begins to fail. So it's better to work within this linear range. than outside this other, outside the linear range. So here's another one when we use standard addition. Here's a standard addition curve for the determination of selenium by fluorescence. So you have intensity here on the y-axis, and you have the concentration, the added concentration. Notice the square brackets stand for molarity, added concentration of selenium in micromolar concentrations. Again, you notice here, again, beyond this, beyond around 2, it fails. So again, this is the dynamic range. The dynamic range is the linear range, the range within which the curve is linear. Now, the other term that we use is the useful range of an analytical method. So in this case here, notice again, this diagram is from a textbook. CM stands for the concentration, the minimum concentration here. Then you start seeing here the LOQ. This is the minimum constant LOQ, 10 times the minimum, the limit of detection. On the x-axis is concentration. Now, you notice the limit of the linear response. This is the limit of the linear response. Beyond here, it starts to fail. It's no longer linear. So the range between LOQ and LOL, so you see LOQ, limit of quantitative, of quantitation, and LOL, limit of linear response. This range here is what we call the dynamic range between those two. So it's a linear range of the calibration curve. Now that we have talked about the dynamic range, we have talked about the limit of detection, and we have had a review of the others. Let's talk about selectivity. What do we mean by the term selectivity? Selectivity is also known as discrimination. What does it refer to? It's the ability to design different yet closely spaced analytical signals. Different yet closely spaced analytical signals. And if you take spectrometers like a SPEC20, it can discriminate wavelengths of light that are about 20 nanometers apart. Even if you can set wavelengths only 5 nanometer difference, it cannot discriminate between wavelengths that are very close. On the other hand, if you have a spectrometer, inductively coupled ICP, an ICP spectrometer, the Varian ICP, Varian is a company. If you have a spectrometer on an ICP, it can discriminate wavelengths of light that are 0.005 nanometers apart. So an ICP has a better selectivity than a SPEC20. Notice it can discriminate wavelengths that are 0.005 nanometers apart. It has good selectivity. The better the selectivity means you can be sure which signal is which when you have more than one analyte in the sample. Because remember, the analyte may absorb a particular light. So this response of that analyte, if they are very close responses, then the better the selectivity can be attained when you can distinguish those signals. So we say the better selectivity means you can be sure which signal is which when you have more than one analyte in the sample. However, if all other conditions are equal, increasing selectivity, because you are decreasing you're discriminating the wavelengths. If you increase the selectivity, that will decrease the amount of signal you can measure. And that will reduce the limit of detection. So as an example, this is an example here from Harris, quantitative chemical analysis by Daniel Harris. So here, in this case, this diagram shows that increasing the monochromator bandwidth, you see, you are increasing the monochromator bandwidth here. You start with 0.1 nanometer bandwidth, you increase it to 0.3 nanometer bandwidth, 0.5 nanometer bandwidth, 1 nanometer, 2 nanometer bandwidth. So you can see, if you increase the bandwidth, the peaks become broad. So increasing the monochromator bandwidth broadens the bands, and it decreases the apparent absorbance. So in this case, this was done here to analyze Brucian 3, PR on the periodic table. So this was one of the elements that has been used, and this was what was observed, the absorbance of PR with a 3+ charge in a crystal of yttrium aluminum garnet. So the point here is the bandwidth is closely related to the selectivity in optical instruments. And is a measure of what range of light we allow to strike the detector at any one given time. So bear in mind, if you have a very narrow bandwidth, yes, you might increase the selectivity between peaks here, as you can see in this orange line here, the wavelengths. If you decrease the bandwidth, you can distinguish the bands. If you increase the bandwidth, the monochromator bandwidth, then you are allowing a lot of light to get to the detector. And that means then you cannot distinguish the band or the peak that you're going to use for your analysis, or your wavelength in this case. So selectivity. Selectivity, as you can see here for the orange line, if you choose this wavelength here, that's a good choice for your analysis because it can distinguish it from other responses from other wavelengths. Now, before we end this chapter, we need to make this clear in instrumental analysis, that everything you do in this class will be a battle. What battle? It's the battle between signal and selectivity. You want a signal, yet you want to distinguish that signal. So everything we do in this class, in instrumental analysis, is the battle between signal and selectivity. But there is no way you maximize both. You have to choose some happy medium where you get enough signal to detect the analyte, but it can also be selective enough so that you are sure of what you are detecting. And that is the battle for analysis between signal and selectivity. And from here, then, I would expect that you will do the fast homework that I post on D12. Thank you.